Shapes of orbitals. After understanding the 4 quantum numbers, let us now move to understand the shapes of these orbitals, which are actually derived from the quantum mechanics. Let us start with the first one, the s orbitals. See, s orbitals, the symbol s is basically has been obtained from the word sharp, and these are actually spherical in shape. So if I draw it like this in the 3 axis, it's the S is like this. So if this is the origin is the nucleus, this is what is 1s we have. Similarly, the 2s will be bigger in size, it will be like this. So this will be your 2s. So these are the shapes of the s orbitals. What is important to note is we try to find out in the shapes of the orbitals the nodes. Nodes are the regions where the probability of finding the electron is 0. So you will always remember, and we have nodes basically of 2 types, angular node and spherical nodes. So angular nodes means the area along any particular angle at which the probability of finding the electron is 0. So always remember angular node, and it is always equal to L. Remember, so L, since L for S is 0, therefore total angular nodes in case of S are 0. And that is how we came to know that they are spherical in shape, because that is the only possible shape we can have if we don't have any angular node. That means we cannot divide this, we cannot have any angle of or a plane along which we can have probability of finding the electron 0. So that's only possible when the shape of the orbital is spherical. P orbitals. P orbitals are double spindle shaped. Basically they have 2 lobes. So their basic shapes are like this. These are called 2 lobes, and always remember both of these lobes are always drawn symmetrically, which shows that the electron density around the nucleus in an atom is uniform. The lines are the point at which these lines crosses, we assume the nucleus to be at this positions. So these are the 2 lobes which are actually of the p orbitals. Now p orbitals we know are of 3 types. We know the value of m in this case is how much? -1, 0 and +1. So it has 3 orbitals. These p orbitals are of 3 types. The p subshell is basically having 3 orbitals, which are actually called px, py and pz. What are their x, y and z represents? Their orientations. So how we draw the shape of the px? If this is what is your 3-dimensional system is x, y and z, this orbital p along the x-axis is called px. Similarly, the one will along y-axis will be your py, and similarly the one along the z-axis will be your pz. So it's basically the p orbitals are having 2 lobes, and they are always, remember, p orbitals are aligned along axis, and they are along axis means one are along x-axis and the other one is along y-axis and the third one is along z-axis. So the p suborbit has 3 orbitals, px, py, pz. Now let me draw the diagram for the pz also. X, y and z, so the pz is like this. What is important to notice that px and py, the value for m for these orbitals are plus minus 1. So if px is plus 1, it will be minus 1. If this is minus 1, this will be plus 1. But the value of pz, the value of m for the pz is 0. So this is how we have minus 1, 0, plus 1, the values of the m for the d3 orbitals. Now, since these p orbitals are having 2 lobes, we can clearly see that this is, I can draw it again so that it becomes very clear. Now, along this we can have a plane where the probability of finding the electron will be 0. So, we say angular node, which is always is equal to n, for p orbitals will be 1. And remember, for px it will be along what? If this is what is your p-axis, this is along yz plane. For y it will be zx plane, for z it will be xy plane. So this is how we can have angular nodes in case of p orbital is always is 1. D orbitals, D word is obtained from the diffused, P was from the principal, S was from the sharp. The D orbitals we know are the divisions of the D suborbit, and we know L, since L for them is 2, the M will have a possible values minus 2, minus 1, 0, plus 1, plus 2. So it has 5 values. So it means what? D is divided into 5 orbitals, which are named as dxy, dyz, dzx, dx square minus y square, and dz square. Now out of these 5, remember, these first 3 are aligned in between the axis, and these 2 are aligned along the axis. So, like P were always aligned along the axis, D are not like this. D are aligned in 2 different patterns. The 3 dxy, yz, zx are along the in between the axis. They are not along the axis. Whereas the last 2, the dx square minus y square and dz square are aligned along the axis. See, all these are the values which we have got on solving that the Schrodinger's wave equation. Now, let us see the basic shape of the d orbitals. D orbitals are having 4 lobed orbitals. 4 lobed means what? Like let us see the structure of dxy. So if this is x and this is y axis, dxy is the orbital which is lying along the xy plane. And now remember, if these are the positive Cartesians along the positive values of the axis, there can be lobes which are along the negative axis. So this is how we have D 4 lobed, and this is the shape of dxy. And from here we can easily make out this particular orbital, the 2 lobes will have a what angular node along this side. This one will have along this side. So the angular nodes will be 2, because we know angular nodes are always equal to L, and L for D are 2. So there will be 2 angular nodes in this case. Let us see the shapes of the other 4 orbitals. The shape of the yz orbital is, if this is your y axis, this is z, this one is your dy z, along in between the axis. They are not aligned along the axis. Next one, the zx. If this is x, this is z, this is dzx. Again align in between the axis, not along the axis. So these were the three ones which were aligned in between the axis. Let us see the shape of the x square minus y square and the z square. Let us see now the shape of the dx square minus y square. See, this is the orbitals which are aligned along the axis. So what we find, if this is x and this is y, this is what is your x square minus y square is. You can take even the third axis, z axis. So nothing is there along the z axis. So dx square minus y square again are four lobed, and they are aligned along the x axis and y axis. Let us see now the dz square. The dz square is having a different shape. This is x, y and z. See, dz square means it is aligned along the z axis and it has a crown shape, a high electron density at the center of it. So the d orbitals is only two lobed, it's not four lobed, and it's having a ring of electron density at the center of it. So this is what is the shape of the dz square orbital is. So this is how we now know the structures of these. Now let us see what is the other type of nodes we can have. As I have told you, nodes can be of two types: angular nodes, which are always equal to L, and there can be spherical nodes which are always equal to n minus L minus 1. The question comes is, what are spherical nodes? Spherical nodes are the areas spherical in shape around the nucleus where the probability of finding the electron is 0. So what we can make out is, see, suppose if this is what is your 1ss and this is what is your 2ss. So this is a sort of a spherical ball we have of 1s, and outer to this one is another spherical ball of 2s. Now this is the area where the probability of finding the electron is 0. So this is called your spherical node. The spherical node, as given by the formula, is always this n minus L minus 1. So if anybody asks you how many spherical nodes does this 2s is having, see, n in this case is 2, L is 0, 1 make it 1. So how many spherical nodes? This one. In a very similar way, if we move to the 3s, we can easily make out between this 2s, 1s, 2s, we were having one spherical node. Between this 2s and 3s, we are again having a spherical area where probability of finding the electron is 0. So again this area is a spherical node. And we can make out how many spherical nodes we have for 3s. One, this shaded region and this shaded region. So we have two spherical nodes for 3s, which we can easily get from this formula, like this: n is 3, L for s is 0, and we have minus, so there are two spherical nodes. So this is how we have spherical nodes as well as angular nodes in the orbitals. Now after understanding the shapes of the orbitals, let us now understand that the number of orbitals in a suborbit are always equal to twice of L plus 1. Number of suborbits in an orbit is equal to orbit number. Number of orbitals in a in an orbit is equal to n square, and since each orbital can accommodate 2 electrons, number of electrons in an orbit is equal to twice of n square. So these are the 4 basic things which we have to always remember. Let us see all this in the form of a diagram. Like suppose this is what is your nucleus is. This is the first orbit we have. This is the second orbit we can have, and this is the third orbit we can have. The first orbit has only 1s, second orbit has 2s and 2p, third orbit has 3s, 3p and 3d. Now, this is what used to call K, L, M and N and so on, the shells or the orbits. Now, how many suborbits do we have in the first orbit? Only 1. How many suborbits in the second? 2. How many suborbits in the third? 3. Now, how many orbitals in an orbit? 1 square is 1. So, orbitals in this case are 1. 2, the square of the 2 is 4. Here 3 plus 1, 4. Square of 3 is 9. This 5 of D, 3 of P and 1 will make it 9. Each can accommodate 2 electrons, so it will make it to have what? How many electrons? 2. Now, how many electrons it can have? In this case, the L1, the 4 can accommodate 2 in each, will make it 8 electrons, and 9, 2 can each will make it 18 electrons. Similarly, in the fourth orbit, we'll be having how many? In this case, 4 4 just 16, and 16 can accommodate 32 electrons. The fifth one will have 25 orbitals, which can accommodate 50 electrons. So that is what we used to write and used to learn in your junior class, that K can accommodate 2 electrons, L can accommodate 8 electrons, and the M can accommodate 18 electrons, N can accommodate the total of this 32 electrons and so on. So this is what is exactly the representation of the orbits, suborbits and orbitals around the atom, around the nucleus in an atom, and we fill the electrons in the multi-electronic atoms in these orbitals, which is actually called electronic configuration.